because the stuff in blue was actually false statements, so I've erased that so we don't look at it. So ionization energy. Ionization energy is the amount of energy required to remove an electron. Okay? If I remove an electron from an atom, what happens to its charge? So I've heard a couple answers here, and now we've heard the whole full spectrum. I understand where you're going with increases. I want you to be more explicit in that statement. So I heard someone say it becomes negative, and I heard someone say it becomes positive. Right? So the increase is technically going to be correct, but I want to hear that positive, negative aspect. Okay? If I remove an electron, well, what charge is an electron? Electrons are negative. When I remove that, it now becomes positive. This is the bane of our existence. That negative sign becomes a challenging thing to deal with. And in the removal of an electron, it's actually a double negative. Okay? So we have to be aware of that and recognize what's happening with our charges. Okay? So if we look at trends in ionization energy, it increases as we go from the bottom to the top in a group. So if I start, I don't know, well, we'll pick with xenon. If I go to xenon to helium, okay, the ionization energy increases. Okay? So it requires more energy to remove an electron from helium than it does from xenon. That's what that statement means. Okay? And the next one, ionization energy increases as we go left to right across a period. So when I go from lithium all the way over to neon, the ionization energy also increases. Okay, so those are the trends. What we want to consider within that is now a couple other statements. Is there anything in those phrases that makes you kind of go, that's not such a good thing to see? Why is in general problematic? Broad term exceptions. There are now going to be exceptions to the trend. Okay? These are general processes, not perfect applications. Okay? And I would argue that what these things are general trends. They aren't the rule. These are actually the exceptions. Okay? The trend comes from understanding what's happening with ionization. Ionization energy is about removing an electron. Okay? Well, where do electrons exist? Outside. Outside what? The nucleus. Anywhere outside? In a gas bubble. No. I think I like where you're going with that.
It's like the sphere, the dumbbell, and the proton.
In individual orbitals. They exist at individual energy levels. Okay, that was the whole point of looking at our electron configurations. The electrons exist at those individual stages. Those were energy levels. The higher energy level we were at, the further from the nucleus we got. Okay? Why did that go to a higher energy? Well, it stopped canceling out the charge. Right? So if we understand where our electrons exist, then we can predict everything with ionization energy, including what the heck is going on with the in general. Right? So that means we would have to look at electron configurations, which is a challenging concept, okay? And it's one I'm increasingly deciding that I just need to not talk about, but I think it's really, really cool. All right, so we're going to keep talking about it, at least for a little while. So if we move through this chart, here's our ionization energy on the left, going up and down, right? And then left to right is our atomic number. So if we start, the very first dot we see is just that black dot. What is that black dot representing?
Hydrogen.
That's hydrogen. Okay? An atomic number of 1, hydrogen. As I move left to right, the next one would be helium, right? There's the helium one. What happened to the ionization energy? It went up. Wasn't that what the trend was? Yeah, left to right it goes up. Fantastic. Then we go to the very next dot, which would be lithium in the next row. And what happened to the ionization energy when I look hydrogen to lithium? It goes down. So if we look down that column, notice that it continues to kind of just decrease down a column. Okay? And it looks weird because that doesn't really look like a column, but that matches our column on the periodic table, yeah? Okay. And then as we look at each of these kind of sections along here, those are individual rows. Okay, so they've inverted kind of on us. Does that make sense? Okay, and as we look through those, we notice that in general, down a column, yeah. Okay, it does decrease. In general, in each of those rows, what happens to it? It increases. So, hey, yeah, in general, that works. Okay, so we do get some weird kind of exceptions. You'll notice some kind of bizarre flatlining through here. What's that bizarre flatlining? Our d orbitals. Okay, d orbitals are tricky and difficult, so
You forget them?
let's ignore them. Okay,
Okay. I like that.
it's nice, isn't it? Okay. The analysis that we're about to go through will work for the d orbitals, but they're a lot more difficult to deal with, so we won't worry about them. Let's look within one of those, right? Which one do you want to look at? Lithium to neon or sodium to argon? Lithium to neon, okay? And so in that case, we'll also delete this one, so we don't have to worry about that. Okay? Because the trend is still going to hold, okay? Or our pattern still holds regardless. And we look lithium to neon, it does increase. Does it always increase?
No.
No, we get this weird drop, and we get this weird drop, yeah? Okay, so the red one, that weird drop was due to what?
It changed to the B.
Beryllium to boron,
Yeah.
and the blue one was
Nitrogen to oxygen.
nitrogen to oxygen. Okay, the explanation for why there's that weird drop is the same for either red or blue. Okay, which is interesting, because when we look at red, what might we say for why it changes?
It changed from S to P.
S to P. So we might say, well, there's a different orbital, and that's why we get this weird change. But nitrogen to oxygen,
It's the same orbital.
it's still all P. Okay? So the change in orbital doesn't actually make sense to explain what's going on here. There's something else at play. Okay? The argument is ultimately the same for both, though I will admit the blue one is more difficult to interpret than the red one. Okay? So I will put it to you guys. Which ones do you want to look at?
More difficult one.
Okay? So we got 50-50 right now, red and blue. Anybody else want to jump in?
You will get the easier one.
That's up to you. It's your decision.
Still be blue.
Blue? Okay. So, the argument behind this, as we said already, had to do with the electrons, which means what do we need to look at? We need to look at the electrons. So let's take a look at nitrogen. Where are the electrons for nitrogen?
7.
There are 7 electrons, but I didn't ask how many, I said where.
Oh, sorry. 2P.
Okay, so we're getting bits and pieces, which is useful. I said, where are they? So give me all of them. Where's the first electron?
On the S.
Where's the second electron?
2S.
Where's the next electron? Where's the next electron?
Anybody other than they're gonna still have a conversation with my.
Okay. You guys understand that? We have to pull to our electron configurations.
Okay. I have to.
Okay. The next part, and this is why this one becomes more challenging, is that our p orbitals are a little bit different than our s. Why are our p orbitals different than our s orbital? There's plural. Okay? So instead of writing it out as this electron configuration, what I'm going to do is go back to the lines that we were using before. Okay? So this 2p3 I'm going to show as each of those orbitals. There's 1, 2, 3 p orbitals. I'm going to place those 3 electrons into those orbitals. Where's the first electron go?
In the first one.
Okay, the first one. Ultimately, it doesn't matter which one. Okay, but let's place it in the first one. Where's the next one go?
In the same one.
In the first one? Why do you say the second one?
What's the question of the first one?
There wouldn't be room. Does anybody want to challenge that? There's not room. How many electrons can fit into an orbital? 2. So there is room, but I like where you're going. When our electrons go into orbitals, they go according to energy. Okay, lowest energy first. If we take a look at those 3 orbitals, they're all the same energy. Except what happens if I put in another electron right next to the first one? It's more energy. Why is that more energy? It already has electron there. There's an electron-electron repulsion. So I'm going to put them in individually first. Then if I have to, I'll double. Right? Okay. So no. Why? They can have to. Okay? You can have more people in your house. Okay? Does that mean you fill your house with people? No. Okay? You want more space. Okay? Another analogy we could use. Okay? You're going to go visit somewhere with a bunch of friends, right? Okay? How many hotel rooms do you get? What's that? Depends how close you are to your friends. Okay, they're your best friend. You get 1 room with 1 bed? No. You get 1 room because they're your good friend and 2 beds. Okay? If your significant other, that's a different system, right?
But there's energy there.
Okay. It could be. But there's a different energy, yeah. There's definitely a different energy associated with that. Okay? If you went with your best friend versus your significant other, there's definitely a different interaction happening there with those beds. Okay?
I'm sorry.
It is. Okay? That's effectively what's going on here. Okay? We're going to space those out as much as humanly possible first. Why do I have 3 beds?
Because I don't want to be close to them.
There's 3 electrons.
Why do I have 3
Because
beds?
of the green.
There's 3 orbital orientations for a p orbital. Okay? If we'd switched it to the s, how many beds do I get? There's 1 bed because there's only 1 orientation for the s orbital because it's that sphere. So this is where all of that electron background comes in and stacks into this.
So like you can think of it as like S is your family, those like your significant other, P is your best friends, and then D is strangers. Is your
Do you usually
Two-
tell
two-
them strangers?
Too distant.
Too much on the metaphor.
Okay.
I mean, when you go
So,
on trips in high school,
what happens when you ionize it?
What happens when you ionize what?
Nitrogen. Ionization energy. It's the energy required to remove an electron. What would my configuration look like? Like, I don't know. What does the red line mean? 1 electron. The definition of ionization energy was remove an electron. What happens when I remove an electron? What does it look like? 2 red lines. Done.
Can you put them both?
That's it. Do we pair? No. Again, you don't pair because that's a higher energy state. Okay? Go evenly first. Okay? Now what happens when we go over and look at oxygen? What is oxygen's electron configuration? 2p4. Same deal, I want to split that down into the electron configuration. How many electrons does oxygen put into those p orbitals? 4. So we go 1, 2, 3, and now I'm going to have to pair. Okay, which one I pair doesn't matter. Typically we read left to right, so we'll pair in that first one. What happens when I ionize this?
You should have 1 in each.
And I will now have 1 in each. Okay? That is actually your answer. That's where people are like, what the hell are you talking about? How does that explain anything? Okay? And this is where we run into the slightly awkward moment. Okay? And to this awkward moment, we're actually going to ask 2 things, or we're going to do 2 things. Number 1, I'm going to tell you should keep facing forward, and you should close your eyes. Okay? And I'm going to walk to the back of the room because half of you aren't going to close your eyes, and that makes this next part awkward. Okay? While you've got your eyes closed, you can envision the most attractive person that you are aware of. Okay? If you covered half of their face and then you're turning around and looking at me, the whole point was to not look at me, was to mirror the remaining side of their face across. Okay? So you're looking at one side of their face, but now duplicated, mirrored to the other side. Okay? What we find is that they look almost identical to if we'd kept their face whole. Okay? And that's an interesting phenomenon. Believe it or not, that is true across the world. Okay? Think about movie stars. Think about actors, musicians. Okay? Everybody that has obtained some level of fame typically has a symmetric face. Okay? And for those of you that might be like, well, that's not really true, okay, we can think of Disney. And Disney has created all sorts of characters. And there was a movie, okay, in Notre Dame that had Esmeralda, and in particular, the Hunchback. What was the whole issue with the Hunchback? He wasn't attractive. Why not? You tried to mirror him? He was exceptionally asymmetrical. That asymmetry is something that constantly perpetuates in our society. Okay, they've done studies behind this. You can open your eyes again. The idea is not to focus at me again, but that's the whole point. Chemistry does the same thing. Let's take a look at nitrogen. I have 3 orbitals. All 3 orbitals have a single electron in them. How symmetric is that?
Very good.
That's pretty dang symmetric, right? Okay. If we look at nitrogen after we ionize, I have 3 orbitals, but now I only have 2 electrons in them. Is that symmetric? No. Okay. So we started symmetric, and as we were alluding to, symmetry meant beautiful. Asymmetry meant Beauty and the Beast? Just pushing it. What happens with oxygen? We had 3 orbitals and now we have 4 electrons in them.
Asymmetrical.
That is asymmetrical. What happens after we remove an electron?
It's symmetrical.
I don't know. It just happened. I was wondering that too, but on my screen I can't see what I did on the other one. Okay. So how does this help us out? Okay, well, ionization energy, I'm going to have to come in and I have to hurt the atom. So imagine yourself as a beauty. Okay, we're all beautiful, but let's just say that's where you are. You're perfectly happy with everything. You're awesome. Everybody's like, oh. Okay? And now I come in with my stick and I say, I'm going to hit you with this stick and I will make you a beast. Okay? And because this is science, I'm just going to do it. Okay? You don't get a choice. Are you going to fight me on that?
Yeah.
Yeah. That's going to require that I put in more energy to cause that to happen. Okay? So what happens with nitrogen's ionization energy? It started beautiful. It's going to become a beast. It's not going to be happy about that. What happens to its ionization energy? It spikes. Okay? Contrast that with oxygen. Okay? Now you're Quasimodo. And I come to you and be like, I've got this stick. I'm going to hit you with it. And you will become beautiful. You become as, well, it doesn't quite work. You become a prince. Right? You become a prince. Okay? Quasimodo might be like, that's gonna hurt. So he's probably still going to put up a fight. But at the end of it, he knows he's going to look like a prince, right? So is he going to put up as much of a fight? No. So what happens to the ionization energy? It drops. The exact point at which that happens is what is causing the exception. Okay? And it happens at very predictable, repeated places. That was transitioning from nitrogen to oxygen. Guess where you can see another exception? Phosphorus to sulfur, arsenic to selenium. Okay? You're like, no way. Take a look at the next one. Okay? It's all off of the electron configurations. Your ionization energy directly comes from understanding where those electrons are placed. Okay? That is a challenging aspect to deal with because you really have to understand atomic orbitals. How comfortable are you with atomic orbitals?
No.
Most people are shaky at best, which means being able to drive to this level of understanding is challenging. This is ultimately the application of all the atomic orbitals. Okay, that's where it's going. Okay, that's kind of neat. And we get to talk about Disney.
So would all the noble gases be beauty sums eventually like them?
If we looked at our noble gases, they all start fully filled, which means they all start beautiful. Are they going to accept being turned into a beast? Nope, which means all of our noble gases should have really high ionization energies. You tell me, are those all really high ionization energies? Okay. And for people saying, well, but argon is still lower, or let's pick xenon is lower than hydrogen. Yeah, xenon's also bigger. You have to evaluate the size of it too. Where's that outermost electron kept? Okay. So this symmetry argument isn't the first thing that goes into it. The energy levels are our first thing that go into it. The next aspect is symmetry behind it. Okay? I think that is a phenomenally cool thing. It's an end application of our electron configurations, but it is a much harder and difficult aspect to nail down.
So I can imagine that you're not going to ask us about the
So, what kind of questions would I ask on this? So first and foremost, do you know what ionization energy is? I actually already asked that question kind of on the test, but I asked it about the next one, electron affinity. What happens to the charge on the atom when I test ionization energy?
it's positive.
It becomes positive because I've removed an electron.
But does it, what if,
It's always going to become positive. Well, what if you add an electron? That's not ionization energy. The definition of ionization energy is I've removed an electron, period. Full stop, it's positive. Done.
it's always gonna
Some are
happen.
positive too. That's not ionization energy. Ionization energy is I remove one electron, period.
So it's always gonna have a proton that removal
Irrelevant.
electron.
Irrelevant. Okay? Any atom I want, if I'm going to ionize it, I'm removing one electron. Any one.
Only one though?
Only one for our first ionization energy officially. Could you remove a second? Yeah, I ionize it once, and then what do? I ionize it again. Could I have a third? Yeah. Why do we not typically look at those? What happens when I ionize hydrogen? How many electrons does it have left? 0. How do I ionize it again? I can't. Okay? So there are limits. A second ionization energy can't evaluate hydrogen because hydrogen doesn't have a second electron to remove. Okay? All of the trends that you see for those come right back to the same principles for the first ionization energy. It's looking at those electron configurations. Okay? The next question that I could ask would be a multiple choice. Which of the following has the highest ionization energy? You might be like, well, damn, I got to figure all that out. No, it's going to be based off the trends. Okay? Looking at the patterns on where there's pseudo-exceptions, that's really hard, right? That would be a really mean thing to ask you as a straight-up standard exam question, wouldn't it?
But you're going to do it anyways.
How will I do it? You actually already know if you read the exam. Extra credit.
Oh, okay.
Okay? So you're not going to be asked to drill that deep. Okay? For the overarching thing. So if you have a hard time with it, that's okay. Just accept it. You don't understand it. You'll learn it later if you need more chemistry. You don't need more chemistry? Who gives a fart? There we go. Is that what you said? Who gives a fart? Okay. And now you're okay. Does that make sense? So you're responsible for those trends and what ionization energy means. Okay. After that, We get electron affinity, which isn't directly addressed in the textbook. Okay? Electron affinity is the energy released to grab an electron. So this is the polar opposite of ionization energy. Electron affinity, we could look at trends on it. It's going to be the same concept as with ionization energy, electron configurations, all that fun jazz. You had a hard time with ionization energy, right? So am I going to ask about electron affinity? No. So what's my question on electron affinity?
Extra credit.
What is electron affinity?
The
What-
opposite ionization.
Not necessarily the trends, though. We got to be careful with that because that's looking at the electron configurations. So I understand where you're going with opposite, but which is the question? Because we said there were two questions for ionization energy. Only one of those questions can you expect for electron affinity.
Oh, which direction?
Direction is a hard one because that requires electron configurations. So it's not that question.
Yeah, every time.
What charge does the atom become when testing electron affinity? It is the ability to attract a single electron from the vacuum. What charge does it become? Negative, because it has now gained an electron. Ta-da! That was the extra credit question on the exam that we threw out because we didn't talk about it. Okay?
In theory, could you just put the electron
So an interesting question there. Does this say anything about more than one element? No. So could we say, well, what happens if I put two elements next to each other and what do they do with that one electron? Yes, it's not electron affinity. It's not ionization energy because both of those are looking more so than just a single element. A single atom is what we're referencing. What happens if I now put a single electron between two atoms and say which one wins? That would be, it's not affinity, it's not ionization energy.
Or negativity.
It's electronegativity. It's the ability for one atom to take an electron away from another atom. That's looking at an electron in a bond. Which way does it go? And I wish I had that here, but I'm pretty sure I didn't put that up there. Okay? So our electronegativity, we already addressed. It's that ability for where does the electron go in a bond. That is a very important concept. Where does it come from? It's effectively the average of our ionization and our electron affinity. Because it's very similar to that. Okay? If one atom's electron affinity is very, very, very high, it's going to start sucking electrons from something else. Okay? So we can determine electronegativity by looking at ionization and affinity. Okay? And that's ultimately where electronegativity comes from. So they're all three very similar concepts, but looking at it from slightly different perspectives. Okay? The next thing I really want to... Oh, that's not the slide I thought it was. I wanted the slide that showed our two different bond categories, because we have two big bond categories right now, right? What are those two bond categories? Ionic and covalent. How do you know you have an ionic bond?
Iron, I mean metal.
Metal and non-metal.
Metal and a nonmetal. How do you know you have a covalent bond?
Non-metal, non-metal.
Two nonmetals. Okay? That becomes very important to us because with that information, I could now look at bonds and how those bonds react. That would be looking at Lewis structure, electronegativity, and all of that. Okay? But now I also want to be able to talk about that. I want to be able to share that information with somebody else. Okay? Which means I have to communicate that information, usually through the written language. Since I know the ionic bond and the covalent bond act very differently, I want different rule sets to explain the naming. So that when I say sodium chloride versus carbon dioxide, I immediately already have clues in those names to tell me I'm looking at ionic versus covalent. Okay? And that's where we encounter our nomenclature. Okay? Which is what you guys went through and did Tuesday. 4 examples. You should be able to do those in about 4 minutes. Get as much information down as you can about those 4 examples. Those people being like, oh my God, 4 minutes, there's no way we can do this. I will actually show you that yes, that is true. Let's start with this first one. This is a metal and a nonmetal. So that's an ionic compound. Nitrogen and oxygen, nonmetal, nonmetal. That would be a covalent compound. Tricarbon dioxide. Carbon is C. Oxide becomes tricky because the ending changed, but that would be O. Both of those are nonmetals. Because they are nonmetals, that would be a covalent compound. Lead is the symbol Pb. Acetate, we could say, is just confusing for the moment. Lead is a metal. Acetate isn't an element up there, okay, which means it's got more, it's a complicated thing. Okay, so in this case, I know that that is some kind of ionic thing. Well, as soon as I've triggered that as being ionic, I know the compound is
Metal dominant.
a metal and some kind of something else. We're looking at ionic. Okay, so now going back and classifying through these. Okay, where I would start is specifying the information I know. Chromium, or Cr, is chromium. O is oxygen, but because it's in a compound, that ending, that suffix becomes "ide." So I've got a chromium oxide. Okay, in the next one, I've got nitrogen.
Are you done with the first one?
Nope. I've got nitrogen, and again, I've got the oxide. Okay. This one I'm actually going to continue through on because I know it's a covalent compound. Those numbers directly go in. 2 is di. 5 is penta. That penta oxide sounds kind of weird to me. If I was forced to, I would probably call it pentoxide, and I think I'm wrong for the record. Okay, I think it is pentaoxide. I think you have to keep the A. It says, the rule says which?
Google says pentoxide.
Pentoxide? Okay, well, cool. Why would I delete it? Because I think pentoxide sounds better than pentaoxide. Okay, which sounds stupid. You named it because it sounded cooler? Yes. Okay,
If we put pentoxide, you will mark it, right?
we'll address that later. Okay, the record, we just delayed like 30 seconds. Carbon, C, with our oxygen, O. Because again, it was covalent, these become numbers. Tri is 3, di is 2. So tricarbon, I have 3 carbons, 2 oxygens. The next one, I actually already started to put some of those pieces together. I have Pb. Because this is ionic, this Roman numeral is reference to the charge on the lead. The lead is a +4. Acetate is something I have to have memorized as C2H3O2. How do I know I have to memorize it? It's on the table of things that I told you to memorize in the video. Have you not watched the nomenclature video? You probably should, because it tells you what you should do. Okay? It is a -1 charge. As I go through and look back at what I've done so far as work, this one's completed, this one's completed. The top one and the bottom one have not been completed. The top one always confuses me, so I'm going to do the bottom one. I have to make sure that when I assemble this structure, I get an overall charge of 0. Okay? I haven't specified the amount of each of these. So I get X lead atoms, Y acetate atoms. Multiple possible solves for that. Okay? Because I don't really know, I'm just going to guess. I'm going to guess Y equals 1. So if I go through and solve that, I would get 4x minus Y. Everybody agree?
Yeah.
Okay. I said Y equals 1. 4x minus 1. Everybody agree now?
Yeah.
Okay. I'm going to add 1 to both sides. I would get 4x equals 1. I'll divide both sides by 4, and I would get x equals 1/4. What did I say x was?
X is 1/4.
X was the number of lead atoms. Can I have 1/4 of a lead atom?
No.
No. So what does that mean? This was wrong. So I'm going to try to guess actually that x was equal to 1. When I go through and do this now, I get 4 minus y equals 0. I would get 4 equals positive y. Yep. Okay, what does that mean? Okay, I guessed x was equal to 1. What was x? Don't tell me 1. The number of lead atoms. I have 1 lead. What was y? Don't tell me 4. the number of acetates. So I could put in 4. C2H3O 24, that doesn't make sense. Let's put in the parentheses to make sure that 4 is delineated away from it. Okay, so now I have that one. I go up to the top one, Cr2O3. I know the overall charge must be equal to 0. Okay, I know I have 2 chromiums times some charge plus 3 oxygens. I'm required to know that in an ionic compound, oxygen will have a -2 charge. I can now solve for x. Add 6 to both sides of the equation. Yep, sorry, I did just cheat to save a little bit of time there. 2x equals 6. Divide both sides by 2. X equals 3. What did I say x was in this case? What about the chromium?
The amount of number of units.
It's not the number of atoms. The number of atoms was already specified in the question as 2. It was the charge on the chromium. That charge gets written into my formula like so. Chromium 3 oxide. We're now at 3608. So I took 5 minutes. 5.5 minutes. Didn't do it in 4. Also look at how much work I've got written versus how much work you wrote on your page.
Oh, wow. The shade, I see.
Okay? This is what you need to be thinking through when you go through and process these. Most of that gets internalized. How does it get internalized? No idea how that would possibly get internalized. Okay? When you step on the accelerator in your car, right, what happens to your car? It accelerates. It moves forward, right? So when you step in your car, you just slam your foot on the accelerator?
No.
No, why not?
Well, depends.
You would take off probably through the parking space, okay, in front of you, and either hit the car in front of you or the car behind you, depending on what gear you're in. So instead, what do? You ease into it. You go slowly. How do you decide how much pressure you have to put on that gas pedal?
Depending on how much clutch you take that away after.
You just know. Okay? So when you sat in the car for the first time, you're like, I just know. Whoop! Perfect every time. That's why when you sit in there with your parents, they're like, oh, God, right? Okay? You didn't just know on how much pressure you had to put on the accelerator. You had to practice. That's how all of these processes become internalized, is with that practice. If you do not do that practice, then yes, this looks like a cluster fart, okay, that you will never be able to get through. Okay? These are just rules that you have to have memorized to do nomenclature, which means do that practice. How much practice do you need? The lab has a nomenclature assignment. It is officially experiment 6 in your packet. It is 5 pages.
Are we going to do that in that?
Actually, I think it's 8 pages of naming compounds, where it is literally you are naming upwards of 100 different things. Okay? Coming up with names or formulas. If you do that assignment as it is intended to be done by struggling your way through showing all this work, you're passable. Okay? Not A, you're passable. Okay? Which means do it again. Okay? Increase that. Where do you find all that practice? The lab is a good place to start. Your textbook has a ton more practice. Almost all of it, you need to know those rules. If you don't know those rules, you need to have an easy frame of reference. Pink Sheet Tutoring Center. Ask for the nomenclature worksheet. They will give it to you. Okay? That's what you need to help organize that process all the way through. That lab we will be doing next week in lab. Okay? And that's all we're going to do. We're going to come in, we're going to sit down, and you're just going to start naming. When you finish that, you could leave early.
And that's number.
We also aren't done here, so.
Number 6.
It's number 6. Number 6 in the lab. You can definitely start it at home. Okay? So, more, you've got practice. Compounds and chemical formulas. What do you see up there?
Something really mean.
really mean and evil and complex, it's probably something that most of you drank this morning.
Caffeine?
It's caffeine, right? It is difficult to deal with a structure that complex. So what do we do to simplify it? We could ignore it. We don't ignore it.
You count how much is
How many carbons are there?
7.
Thought it was 8, but I'll accept 7. Hydrogen. How many hydrogens are there? Are there 8?
Yeah, 8, sorry, my bad.
Hydrogens. I'm going to accept 10.
Yeah.
Nitrogens. Oxygens. 2. So when we're looking at a formula, it's literally just counting the atoms in that molecule. That's the point of the formula. I'm just
There are 4.
trusting your counting.
So,
Okay.
the connections, do we just read it?
So when determining the connections, you don't have to. When do you have to determine those connections? Actually, never. Okay? You don't need to stress about those connections. What you need to stress about is the meaning behind it. The meaning goes into your formula. That's what you need in a formula. Okay? So if we look at the language of formulas, you've seen them before. H2O, what did that mean?
Water.
Water and what else?
It's a covalent.
Covalent bond. Cool, I accept that. Because hydrogen and oxygen are both nonmetals. It has no other meaning? Phase isn't specified, so I won't accept aqueous.
Solvent.
If you dig really deeply, you can get to the number of electrons. It's a lot easier than that. You don't have to dig that deep. You guys are trying way too hard. The number of elements present. There's 2 hydrogens, 1 oxygen. It literally tells you that in the formula. That's why we go to formulas.
I was going to say
How many atoms are in C6H6O6?
18.
18. 6 plus 6 plus 6. You know? Yeah. I always make other references. Okay? How many hydrogens in this formula?
8, 4. You're asking hydrogen, right?
Hydrogens, yeah.
4.
Okay, why not 3? I only see H3. Why did we pull that H out? It's the same element. Why not leave it in there? Why not write the C2H4O2?
Because it's 2 compounds together.
It's next to the
Question mark.
If we've done our nomenclature homework, acids have a hydrogen in front and the aqueous in back. By pulling that hydrogen out, we're now tipping off whoever's reading that you're looking at an acid. So our formula can encode all sorts of different information. It's not just the number of atoms, but sometimes the placement of those atoms can key you off to different pieces of information.
So if it's more, what would it be? Would it be like different? Or would it be
If it says C2H4O2, does that change the compound? Maybe, maybe not. That's the problem with formulas, is formulas don't tell you the connectivity of the individual atoms. Okay? So that's why we sometimes change the formula to give information about its reactivity. Sometimes. Sometimes we choose not to. Why not? Because humans are fickle. And we change our mind depending on what we're trying to represent. Kind of like what you do when you write. Okay? What you write to your mom is probably significantly different than what you write to us. Hopefully. Okay? So we're going to change our representation of that information for different audiences and for different purposes.
The CHO, isn't that acetate? Would that be considered hydrogen acetate as like an acid, or is that?
C2H3O2 should stand out as kind of a red flag because we literally just covered that. Yeah, that would be acetate. So by writing the formula in that fashion, I can draw attention to the fact that I have that complex ion. If I embed the hydrogen into it, do I see clearly that acetate is present? No. That doesn't mean it's not present. It just means I can't tell that information. So we will change our formulas to represent what we are trying to convey. Okay, what is the purpose as chemists are we trying to represent? Okay, we see that show up in chemical reactions as well. Okay, where we place things, what symbols we use, allows us to change and interpret different aspects of information. Okay? I did see the question, Tasha, I'll come talk to you, but unfortunately